Welcome to the online learning initiative of AKPCTA Learn in Lockdown. I am Dr. Vidya from SN College Kollam. I am dealing with the topic carbon nanostructures from the paper Nanoscience and Technology. Carbon nanostructures. Carbon nanostructure consists of various low-dimensional allotropic forms of carbon including carbon black, carbon nanotubes, fullerenes, graphenes, carbon fibers, etc. In this lecture, we are going to discuss about carbon nanotubes and fullerenes. Fullerenes or Buckminster fullerenes are allotropes of carbon in which carbon atoms are connected by covalent bonds to form closed structures having carbon rings. These molecules can take the shape of a hollow sphere, ellipsoid, tube, or any other shape of any size. Structure of fullerenes. Fullerenes consist of 60 carbon atoms connected by single and double covalent bonds to form closed structures. They have tourniqueted icosahedron structure which resembles the geometric coordination of a saucer bowl having 12 pentagonal and 20 hexagonal faces. Its lattice is FCC. Each C60 molecule is connected by van der Waals force with a separation of 1 nanometer. The figure shows a fullerene in which carbon atoms are connected by covalent bond to form pentagonal and hexagonal rings. There are many types of fullerenes. Smaller fullerenes are those having less than 60 carbon atoms, example C20. Larger fullerenes has more than 60 carbon atoms, example C80. Not only carbon, but pure forms of silicon and nitrogen can also form ring-like structures. They are used in quantum computers, catalysts, and superconductors. N20 is an example for this. They are known as buckyballs. Carbon nanotubes. Carbon nanotubes are invented by Ichimo Sumio of Japan. They are cylindrically large molecules consisting of hexagonally arranged sp2 hybridized carbon atoms. They can be thought to be formed by rolling a graphite into tube with the ends of the sheet bonded together. Their exceptional physical properties, tubular structure, high surface area, and aspect ratio make them ideal for many potential applications. There are two types of carbon nanotubes, single-walled carbon nanotubes and multi-walled carbon nanotubes. Single-walled carbon nanotubes consist of sheet of graphite rolled up to form hollow tube with walls of 1 atom thick. They are single-layer, one-dimensional materials. It is observed as two planes under a transmission electron microscope. They have high surface area and aspect ratio. Its diameter is nearly 2 nanometer and length 100 micrometer. They are also known as carbon nanowire. In multi-walled carbon nanotubes, the walls are formed by multiple 1 atom thick sheets of graphite. They are multi-layer. They are observed as concentric pattern around the smallest nanotube. They have high aspect ratio. Figure shows a single-walled and a multi-walled carbon nanotube. Fabrication. There are mainly three methods for the fabrication of carbon nanotubes: laser evaporation technique, carbon arc method, chemical vapor deposition. In laser evaporation technique, a graphite target is heated using a laser beam which is then condensed on a cooler surface. Single-walled carbon nanotubes are made using this technique. Carbon arc method contains negative carbon electrode which sublimates due to high discharge temperature. Multi-walled carbon nanotubes are prepared using carbon arc method. In chemical vapor deposition, a hydrocarbon gas is decomposed and which is then deposited on a suitable substrate containing catalyst. Tubes with the open ends are produced in this method. It is most favorable for large-scale production. Structure. Structure of a carbon nanotube can be explained on the basis of two quantities, chiral vector and chiral angle. Chiral vector is defined in terms of lattice indices and unit vectors. Ch equal to Na1 plus Ma2, where N and M are integers representing the number of steps along zigzag carbon bonds. Chiral angle is the measure of twist of the carbon nanotube. It is given by sin theta equal to root 3m by 2 into root of n square plus m square plus nm. Based on the magnitude of chiral angle and chiral vector, carbon nanotube have three structures. When chiral angle is 30 degree, it has armchair structure. When chiral angle is 0 degree, it has zigzag structure. When chiral angle is between 0 and 30 degree, it has chiral structure. Figure shows the carbon nanotubes of three different structure: armchair, chiral and zigzag structure. Electrical properties. Carbon nanotubes may be metallic or semiconducting depending on the diameter and chirality of the tubes. Metallic tubes have armchair structure, whereas semiconductor tubes have zigzag or chiral structure. As diameter of tube increases, band gap decreases. In metallic state, conductivity of nanotube is very high and is of order billion ampere per centimeter, which is much higher when compared with the best metal conductor. Passage of high current do not heat up the carbon nanotubes. Here is a comparison between conductivity of copper and carbon nanotube with respect to temperature. We can see that as temperature increases, the conductivity of copper decreases, whereas the conductivity of carbon nanotube remains as such even if the temperature increases. Electron transport property of the tube takes place by means of electron tunneling. Electrons in the tube are not localized. They are spatially extended over the large distance about the tube. Electron wave function of a carbon nanotube has a donut shape, so defects cannot produce localization. In multi-volt carbon nanotubes, interval reaction redistribute the current over individual tubes non-uniformly. But in single-walled metallic carbon nanotube, no change in current is observed. Defects allow the single-walled nanotube to act as transistors. Carbon nanotube shows negative magnetoresistance at low temperature. Vibrational properties. Carbon nanotubes have two modes of vibration, A1G mode and E2G mode. A1G mode represents the in and out vibration of molecules along the diameter of the tube. E2G mode represents squashing of tube skews us down in one direction but expands in a perpendicular direction. Both the modes are Raman active. Frequency of the vibration depends on the diameter of the tube. From the graph, we can see that as diameter of the tube increases, frequency decreases. Mechanical properties. Carbon nanotubes have very good mechanical properties. Because of few defects, they are very strong. They possess large Young's moduli which make them very stiff and hard to bend. When they are bent, they buckle back and can be straightened without any damage. This is because of the fact that carbon atoms in hexagonal rings are sp2 hybridized. When they bend, they change their structure and rehybridize without breaking. Carbon nanotubes possess very high tensile strength of about 45 billion Pascal, which is much higher value when compared with that of steel. Now we can see some of the application of carbon nanotubes. First one is field emission and shielding. When a small electric field is applied parallel to the axis of carbon nanotube, electrons are emitted at very high rates from its end. This is called a field emission. This property finds application in flat panel displays of computers and televisions, where it is used as electron gun to imprint electrons on the phosphor screen. High electrical conductivity means poor transmitters of electromagnetic radiation. This is termed as shielding. This property can be used to protect our electronic gadgets like computers from the attack of electromagnetic radiation emitting weapons. Next, computers. Carbon nanotubes serves the purpose of field effect transistors and switching components in computers. Very fast switching time makes the processor works more faster and effectively. More switches can be placed on a single chip as the carbon nanotube is small in size. Carbon nanotubes carry large current without heating up so quickly, so it can be used as interconnects, which do not melt on passage of high current. The thermal conductivity of carbon nanotube is high, so it can act as heat sinks which rapidly transfer away heat from the chip. Fuel cells. A fuel cell is a device which converts chemical potential energy to electrical energy. Carbon nanotubes found application in fuel cell technology also. In lithium electrode fuel cell, charge carrier can be stored inside the carbon nanotubes. Carbon nanotubes can be used in storing hydrogen also, which is the future fuel for automobiles. Hydrogen is stored inside the tube by electrochemical cell reaction, in which carbon tube serves as the negative electrode, nickel hydroxide serves as the positive electrode, and KOH as the electrolyte. Water of the electrolyte decomposes to hydrogen ion and get deposited on the carbon nanotubes. Chemical sensors. Carbon nanotubes can be used as sensors. Semiconducting carbon nanotubes senses gases like methane, ammonia, nitrogen, etc. When a gas is passed through a carbon nanotube placed in an electric field, its conductance increases. This is because charge transfer takes place between carbon nanotube and gas passed. Also, on passage of gas through the nanotube, its Raman modes get shifted. By analyzing the shift in Raman mode, we can identify the gas passed through. Catalyst. Carbon nanotube can act as catalyst in many reactions. For example, hydrogenation of cinnamaldehyde in liquid phase, reduction of nickel oxide and aluminum chloride, formation of MoO2 and cadmium sulfate. Mechanical reinforcement. Because of high tensile strength, ability to bind with fiber, high aspect ratio, carbon nanotubes are ideal for composite reinforcement. For example, aluminum or polypropylene can be mixed with the carbon nanotube, which enhances its mechanical property to a greater extent. Carbon nanotubes have atomically smooth surface, so there is no strong interface interaction between materials mixed together. Carbon nanotubes form strong bonds with iron, so it can be used to reinforce steel, which is 7 times stronger than ordinary steel. Thank you for listening. All the best for your exams.